This is Chapter 2, Lesson 3. Today we're going to talk about J.J. Thomson and Lord Ernest Rutherford. So, experiments by several scientists, specifically the ones we're going to talk about are J.J. Thomson and Ernest Rutherford. In the late 1800s, they changed Dalton's atomic theory. So, Dalton at the time had thought that atoms were the smallest particles in the universe. And then later on, Thomson and Rutherford came to discover particles that were smaller than that. And so the discovery of the electron was made by J.J. Thomson. And what he did was he took a glass tube and he pumped a lot of the air out of it, applied voltage to metal plates called electrodes. There was the anode and the cathode, right? And so the anode is the metal plate that had a positive terminal, and so it was positively charged. And then you have the cathode, which was the negatively charged terminal. Okay, and so what J.J. Thomson then discovered, and if you click on this link, it'll tell you about J.J. Thomson's life, which is completely fascinating. He is a brilliant individual, and you get this is what a cathode ray tube kind of looks like. So you have your cathode over here, which is your source of electrons, and then your anode over here, which is your positively charged plate, and the electrons move from the cathode to the anode. Thomson discovered that if you put a small hole in the anode, then you get a more focused beam of particles, and your cathode ray is stronger, right? And so J.J. Thomson was not the first to use the cathode ray tube, but he made a lot of discoveries based upon this cathode ray tube. And what he observed was that these rays, he called cathode rays because they emanated from the cathode, could be used to do things. Okay, and we used cathode ray tubes as a light source in early television sets, computer monitors, and radar displays. It's not used any anymore, but if you check in your grandparents' house, they may have a tube television, and those giant, heavy tube televisions use cathode ray tubes as their light source. And so the cathode rays were negatively charged, and Thomson determined this because they were attracted to positively charged um, electric electric fields, and they were also attracted to magnets. And so he determined that the beam was made up of charged particles. And he also when you put a paddle wheel in the way of the cathode rays will strike the paddle wheel and it will turn it, right? And so that must mean that the particles have mass, right? And so Thomson's experiments showed that cathode rays consist of particles that have mass and have a negative charge. The, they were later called electrons. I'm not sure that Thomson called them electrons. I believe he called them corpuscles. Um, but the electrons have a negatively charge. He also determined that these come from atoms and that electrons are identical, um, irregardless of the atoms that they come from. So if he filled his cathode ray tube with different gases, the electrons would be exactly the same. And Thomson was actually able to determine the charge to mass ratio for the electrons very precisely using electric fields and magnetic fields. And he used the fact that he would um, curve the path of the electrons with the electric field and then straighten it again with the magnetic field and the strength of those fields to determine what the mass to charge ratio of the electrons was. And so he came up with this model of the atom that's called a plum pudding model because he said, though there's these negative electrons that must exist in atoms, right? But there must be a positively charged cloud of space in that atom because atoms are neutral, right? And so he hearkened this to an English dessert called plum pudding. Um, Pudding, by the way, in case you don't know, in England any dessert is called a pudding. And so if you make a cake with plums in it, this is like a fruit cake. It's a really gross thing, but most British desserts are gross by American standards. However, that it would give you a visualization. So if you imagine a fruit cake with little shreds of plum in it, the little shreds of plum are the electrons in his model, and then the spongy cake is the rest of the positive charge of the atom, according to Thomson's model. And then a student of Thomson was Ernest Rutherford. Ernest Rutherford was born in New Zealand and then traveled to Thomson's lab when he was a graduate student. And then later on, he moved to McGill University in Canada, did a lot of research there, and eventually moved back to England to study with Thomson again. In the meantime, Ernest Rutherford discovered alpha and beta radiation. He identified radioactive isotopes. He discovered the radioactive element radon, which is a noble gas, and he discovered isotopes. So in the meantime, in between, him uh, being with Thomson and then leaving Thomson, and then coming back to Thomson, Rutherford did a whole bunch of stuff. But in 1911, he conducted the famous gold foil experiment, and where he shot alpha particles, which was a type of radiation, at gold foil, and discovered that the plum pudding model was not correct, that there was some sort of dense region of positive charge within an atom. And so these alpha particles were beams of positively charged particles. They were directed at a thin sheet of gold foil. The reason why I used gold is because gold is very malleable and you can hammer out gold into very thin sheets of gold foil. Think of like gold leaf, right? Um, very thin sheets of gold. And you can measure the angles that the alpha particles were deflected, and he determined the size of the um, nucleus of a gold atom. So this is kind of an illustration of what it looks like when your alpha particles, these green lines, hit the atoms of gold. And so these are atoms of gold because they're gold colored, right? And you have the small, dense nucleus in the middle, but then you have this mostly empty space where occasionally you'll find electrons. And so when the alpha particles come close to the nucleus, they're deflected from it. And when they hit the nucleus more head on, they were reflected by it. And so this led to some conclusions. So there's a source of radioactive alpha particles in here, and that is being shot at your thin gold foil. Then you have a fluorescent screen around the gold foil so that you can detect when those charged particles hit the screen. Okay. And so Rutherford determined that there must be a nucleus to the atom. The nucleus is the only thing that would deflect these highly uh, or quickly moving alpha particles. And since the alpha particles are positively charged and they were repelled, they must also be, the nucleus must also be positively charged. And so the reason why most of the alpha particles went through the gold foil is because the nucleus must be a very small region in the atom, and that most of the atom is empty space. And so if you look at this blown up view of the atom where alpha particles are possibly hitting it, right? You have most of the alpha particles going straight through, not hitting anywhere near the nucleus, right? But if you get close to the nucleus, boom, you get deflected. And if you hit the nucleus head on as an alpha particle, you would get reflected. And so now we know that the nucleus is the dense central portion of the atom, and that the nucleus is made up of protons and neutrons. They didn't know that at the time, that it was made up of protons and neutrons. I mean, Thomson took Rutherford's work and then worked out the existence of protons. But at the time, right? They didn't know exactly what was causing this. But now that we know this, we know the nucleus also contains all of the positive charge and nearly all of the mass, but a very small fraction of the volume of the atom. If you remember from the atoms, isotopes, and ions Pogel, that the nucleus of the atom is much, much, much smaller than the space that the atom occupies, right? And that's because electrons travel around in very large orbitals where most of it is empty space. And so Rutherford changed Thomson's model and put a nucleus in the middle of it. Now, at the time, they couldn't understand why the electrons were not tumbling into the nucleus because the electrons were negatively charged, right? Nucleus is positively charged. Electrostatic attraction would cause the electrons and the electrons to fall into the nucleus, right? But later on, we discover why that is. Okay, but I'll leave that for later. I won't. I don't want to spoil it all for you right now. So here's a really cool video that I showed you before about um, John Dalton. This summarizes again the um, what evidence has led us up to this point.